Welcome back, everybody. Ready for another deep dive? Today, we're going to the cutting edge of nanoscience with this fascinating paper. It outlines how researchers are using diamonds to study the world at the atomic level.
Diamonds.
Yeah, diamonds. It's all about a technique called NV-NMR spectroscopy.
Absolutely. What's really exciting here is how scientists are merging quantum physics with chemistry, to unlock those secrets of the nano world.
Okay, so we're talking diamonds, but not the kind you'd find in a jewelry store, right?
Right.
These diamonds have tiny imperfections called nitrogen-vacancy centers or NV centers.
Those V centers.
Yeah, what makes these imperfections so special?
Well, these NV centers are like incredibly sensitive antennae. Think of them as tiny spies embedded within the diamond
Okay.
that can detect the faintest whispers of atoms and molecules nearby.
Wow.
This ability to sense at the atomic level, that's the heart of NV-NMR.
So it's like having a super-powered microscope, one that can see individual atoms dance around.
Kind of.
Yeah. Sign me up. But I know traditional NMR uses fairly large samples. How are they using NV centers to study things at the nanoscale? I mean, like surfaces, interfaces, or even single molecules.
Well, that's the challenge researchers have been grappling with for years, how to shrink NMR down to the nano world.
Yeah.
And this paper highlights a major breakthrough in doing just that, achieving incredibly high resolution at the nanoscale.
Okay, I'm hooked. Tell me more about this breakthrough.
All right, well, to understand the significance, we need to appreciate the two different worlds of NV-NMR, the microscale and the nanoscale.
Two worlds of NV-NMR. What's the difference?
Think of it like this. On the microscale, we're dealing with relatively large sample volumes. We use powerful magnets to align the spins of the atoms in the sample. This alignment, it's called thermal polarization. It creates a clear, coherent signal, like a well-rehearsed choir singing in perfect harmony.
That makes sense. So in the microscale world, we get strong, clear signals because all the atoms are on the same page. But what happens at the nanoscale?
Things get a lot messier at the nanoscale. Instead of that beautiful harmony, you have what we call statistical polarization. It's more like a bunch of individuals all singing random notes at different times.
So it's a much noisier environment at the nanoscale. Is that what's been blurring the signals in nanoscale, NV and MR?
Exactly.
Right.
And to make matters worse, at the nanoscale, you're dealing with molecules constantly diffusing. They're bouncing and jiggling around like bumper cars.
Oh, wow.
This constant motion makes it incredibly difficult to get a clear picture of what's happening.
So how did the researchers overcome this diffusion problem? Was it some super sophisticated technique?
Well, it started with a clever simulation. They modeled a single spin, like a tiny compass needle,
Okay.
randomly bouncing around near an NV center.
I'm picturing one of those bouncy balls in a bingo machine, pinging off the walls.
Exactly.
So what did they learn from watching this simulated spin dance around?
Well, the simulation highlighted a crucial difference in timescales between the microscale and the nanoscale. In the microscale, the spin precesses. It wobbles like a spinning top, much faster than it diffuses.
Right.
This fast precession leads to a distinct signal that's easy to pick up.
So it's like trying to take a picture of a spinning top. If it's spinning fast enough, you get a clear picture of the blur. But what happens at the nanoscale? Does the spinning slow down?
Not exactly. At the nanoscale, the spin is still precessing, but now the diffusion, that random bouncing around, is happening on a similar timescale. It's like trying to take a picture of that bingo ball while it's bouncing around. You just get a blurry mess.
That makes sense. So the diffusion at the nanoscale was essentially drowning out the signal from the precessing spins? But they found a way to overcome this, right? What was their secret weapon?
Their aha moment was realizing that even though the signals from individual spins are getting jumbled by diffusion, the overall signal from a uniformly polarized sample remains detectable at the nanoscale. Think of it like this. You might not be able to pick out individual voices in a noisy crowd, but you can still hear the roar of the crowd itself.
So they figured out how to listen to the roar of the nano crowd, even though they couldn't hear the individuals. That's pretty clever. So how did they put this insight into action?
They designed a brilliant experiment. Using a diamond chip with shallow NV centers, placed just nanometers below the surface.
So they brought the NV sensors incredibly close to the action where the nanoscale dance was happening. What else was in their experimental setup?
They cleverly combined this diamond chip with microfluidics, tiny channels for precisely controlling the sample, and a powerful magnet to align the spins. But they needed one more trick up their sleeve to boost the signal, a technique called ODNP.
ODNP?
Yeah, or Overhauser dynamic nuclear polarization.
Okay, break that down for me. What exactly does ODNP do?
Imagine you're trying to hear someone whispering in a noisy room.
Okay.
ODNP acts like a megaphone, amplifying the whispers of the nuclear spins, making them much louder and easier to detect.
Ah, so it's like turning up the volume on the nano crowd? That's brilliant. So they had their diamond chip microfluidics to control the sample, a powerful magnet, and ODNP to boost the signal. What happened when they ran the experiment?
First, they calibrated their setup with a microscale diamond, essentially setting a baseline for comparison.
Okay.
Then they swapped in the nanoscale diamond, keeping everything else the same.
Yeah.
A classic controlled experiment.
So they were comparing apples to apples, or rather diamonds to diamonds. What were the results? Did they manage to overcome that diffusion barrier?
The results were astounding. They achieved single-digit Hertz resolution in the nanoscale NV-NMR spectra of water.
Wow.
That's a huge EE leap forward, like going from a blurry photograph to a crystal clear image.
Wow, single-digit Hertz resolution. That's incredible. But what does that mean in practical terms?
It means they could now distinguish tiny differences in the frequencies of the nuclear spins, giving them a much sharper picture of the molecular environment at the nanoscale. To give you an idea of just how sensitive their technique was, they achieved a sensitivity of roughly 20 femmelhertz for approximately 30,000 individual NV detection volumes.
I'm going to need you to unpack that a bit. What does that sensitivity value actually tell us?
Think of it this way. They could detect an incredibly small number of molecules, a tiny droplet compared to the volume of an Olympic-sized swimming pool.
Oh.
This incredible sensitivity opens up a whole new world of possibilities. We can now study minute samples like a single layer of molecules on a surface, something that was simply impossible with traditional NMR.
So they essentially created a nanospy network, able to eavesdrop on the conversations of individual molecules. That's mind-blowing. But did they only study water? Could they apply this technique to other molecules?
They didn't stop at water. They went on to test their technique on a more complex molecule called trimethylphosphate. And guess what? They were able to achieve similar resolution, even resolving something called scalar coupling.
Hold on, scalar coupling. Refresh my memory. What's that again?
Scalar coupling is basically a delicate dance between the nuclei within a molecule. Imagine two tiny magnets spinning near each other. Their spins influence each other, creating subtle shifts in their frequencies.
Okay.
Being able to resolve this coupling at the nanoscale is a testament to the incredible resolution of their technique.
So not only could they detect the roar of the nano crowd, but they could even hear individuals whispering to each other within that crowd. That's amazing. But this technique focuses on detecting coherent signals. I've heard about another approach called spin noise detection that focuses on the randomness of the spins. How does this new technique compare to that?
That's a great question. Spin noise detection is a valuable tool, especially for certain applications. It's a faster approach and works well at low magnetic fields, but it's not as sensitive. Think of it like eavesdropping on a whispered conversation versus having a clear phone call.
So spin noise detection is like trying to pick up snippets of a conversation through a wall, while this new technique gives you a direct line.
That's a good analogy.
Yeah.
The researchers speculate that spin noise might be better suited for studying solid materials where the spins are more sluggish, like a slow-moving crowd. But for liquids where the molecules are constantly bouncing around, coherent detection with hyperpolarization, that megaphone effect is the way to go.
So it's all about choosing the right tool for the job. And this breakthrough gives scientists a powerful new tool for exploring the nano world. Before we dive into the potential applications of this technique, let's take a quick recap of what we've learned so far.
Absolutely. The big takeaway here is that researchers have cracked the code to high-resolution NV and NMR at the nanoscale by cleverly combining several techniques. They use shallow NV centers to get close to the action, microfluidics for precise sample control, a powerful magnet for spin alignment and ODNP to amplify the signal. And most importantly, they recognize that by focusing on the overall signal from a uniformly polarized sample, they could overcome the blurring effects of diffusion at the nanoscale.
It's a remarkable achievement, opening up a whole new avenue for exploring the nano world with unprecedented clarity. Now I'm dying to know, what are the potential applications of this breakthrough? What mysteries can we now unlock with this level of sensitivity?
That's what we'll delve into in the next part of our deep dive. We'll explore the exciting possibilities of this technology in fields like materials, science, biology, and medicine. But before we jump in, I'd like to leave you with this question to ponder.
Ooh, I love a good cliffhanger. What's the question?
If you could use this nanospy network to explore any material or system, what would it be? What secrets would you want to uncover at the atomic level?
All right, I've been giving that question some thought. And honestly, My mind is buzzing with possibilities. It's like being handed a key to a whole new world. But before we get lost in the what-ifs, I'm eager to hear about those real-world applications that are already within reach. Where do you see this technology making the biggest impact first?
Well, it's hard to pick just one area, but I think material science is a prime candidate. Imagine being able to zoom in on the interfaces between different materials with atomic precision, something that's been a black box for a long time.
Yeah, interfaces are fascinating. It's like where the real action happens, right? Whether it's how electrons flow between materials in a solar cell or how molecules react on the surface of a catalyst, what kind of insights could we gain from studying interfaces with this level of detail?
Think about battery technology. We could finally understand the processes happening at the electrode-electrolyte interface, where the energy transfer actually occurs. Being able to pinpoint exactly what's happening at the atomic level could lead to huge improvements in battery efficiency and lifespan.
So longer-lasting batteries for our phones and electric cars, I'm already sold. But I bet the applications go way beyond batteries.
Absolutely. Consider the field of catalysis. So many industrial processes rely on catalysts to speed up chemical reactions. But often, we're just guessing about where those reactions are actually occurring on the catalyst surface.
So we're throwing a dart in the dark, hoping it lands on the bullseye. Seems like a pretty inefficient way to design catalysts.
Exactly. With nanoscale NV-NMR, we could pinpoint the exact active sites where the magic happens, the precise atomic arrangements that make a catalyst effective. This knowledge could revolutionize how we design and optimize catalysts, for everything from producing clean energy to manufacturing new materials.
Wow, it's amazing to think that something as tiny as an NV center could have such a huge impact on industries like energy and manufacturing. But I know you're also excited about the potential of this technique in biology. What kind of biological mysteries can we now start to unravel?
One area I'm particularly excited about is understanding how proteins interact with cell membranes. These interactions are crucial for a vast array of cellular processes, from signaling to nutrient transport. But they happen on such a tiny scale that they've been incredibly difficult to study.
So it's like trying to eavesdrop on a conversation happening behind a closed door.
Precisely. But with nanoscale NV and MR, we can finally get a clear view of what's happening at the membrane surface. We can see how proteins dock with receptors, how molecules pass through channels, and even how drugs interact with cell membranes.
That could revolutionize drug development, right? Being able to see exactly how a drug molecule interacts with its target on a cell membrane.
Exactly. We could design drugs that are more targeted and effective, with fewer side effects. And it's not just drug development. This technique has the potential to unlock a deeper understanding of so many biological processes, from how cells communicate to how viruses infect their hosts.
It feels like we're on the verge of a whole new era of biological discovery. But there's one application that I'm particularly fascinated by, the potential to study single molecules. Is that really a possibility with this technique?
Achieving single molecule sensitivity is the holy grail of NV-NMR. And while it's still a challenge, this breakthrough brings us significantly closer to that goal.
What would be the implications of being able to study the structure and dynamics of individual molecules?
Imagine being able to observe the folding and unfolding of a single protein in real time. It'd be like watching a tiny origami master at work, revealing the intricate dance of atoms that gives a protein its unique shape and function.
That would be incredible. Talk about unlocking the secrets of life itself. But it's not just about fundamental understanding, right, Hal? Single molecule sensitivity could also have huge implications for medicine.
Absolutely. Imagine using NV sensors as tiny probes to detect biomarkers for diseases like cancer. We could potentially identify these markers at much earlier stages when treatment is more effective.
So instead of waiting for a tumor to grow large enough to be detected by current methods, we could find the first few rogue cells, potentially stopping cancer in its tracks.
That's the vision. And with single molecule sensitivity, we wouldn't need invasive biopsies. We could detect these markers from a simple blood draw or even a breath sample.
Wow, the possibilities are truly mind-boggling. But I realize we've been painting a pretty rosy picture here. What are some of the challenges that still need to be addressed before this technology reaches its full potential?
One key challenge is improving the sensitivity even further. They've achieved remarkable sensitivity for nanoscale measurements, but we need to push those limits even further, especially if we want to reach single molecule sensitivity.
So it's a constant race to improve the signal-to-noise ratio, to hear those whispers even more clearly. What else stands in the way?
Another challenge is developing more robust and user-friendly NV and MR instruments. The current setups are quite complex and require specialized expertise.
So it's like having a powerful telescope that only a handful of astronomers know how to use. We need to make this technology more accessible to a wider range of researchers if we want to see its full impact.
Exactly. Making these instruments more user-friendly, compact, and affordable will be crucial for accelerating the adoption of this technique in various fields.
So we need to go from bespoke telescopes to mass-produced smartphones, so to speak. What about the quest for single-molecule NMR? What are the biggest hurdles there?
The challenge with single-molecule NMR is not just about sensitivity. It's also about being able to control and manipulate individual molecules with incredible precision. We need to be able to hold those molecules steady, like pinning them down under a microscope, so we can study their structure and dynamics in detail.
So it's like trying to perform surgery on a single atom. It sounds incredibly challenging.
It is. But researchers are working on clever techniques to trap and manipulate single molecules, using things like optical tweezers or nanopores. Combining these techniques with the high resolution of NV-NMR could finally unlock the secrets of single-molecule behavior.
It's an exciting time to be following this field, but I know there's a whole other area of potential applications that we haven't even touched on yet. The world of quantum sensing. I'm eager to hear about how NV centers are being used to push the boundaries of quantum technology. Quantum sensing, it sounds so futuristic. Makes me think of teleportation and time travel. But seriously, what exactly is quantum sensing, and how do NV centers fit into all of this?
Well, it's not quite teleportation or time travel, at least not yet. But quantum sensing is a rapidly growing field that uses the principles of quantum mechanics, to measure things with incredible precision. And it turns out that NV centers in diamonds are exceptional quantum sensors.
Okay, so they're not just good for studying molecules at the nanoscale, they're also quantum superheroes. What makes them such good sensors?
Remember how we talked about those NV centers being like tiny spies embedded within the diamond?
Yeah.
Well, they're not just passively observing. They're incredibly sensitive to their surroundings,
Okay.
their quantum state. Think of it as their mood can be easily influenced by things like magnetic fields, electric fields, temperature, even pressure.
So it's like they have a sixth sense, like a heightened awareness of their environment at the quantum level.
Exactly. And by carefully measuring how their quantum state changes in response to different stimuli, we can use them to detect and measure those stimuli with remarkable precision.
That's pretty impressive. But what are some real-world applications of this quantum sensing ability? Give me some examples that will blow my mind.
Get ready to have your mind blown. One application that's already making waves is using NV centers to create ultra-sensitive magnetic field detectors. These detectors are so sensitive they can pick up the magnetic fields produced by individual electrons, something that was considered impossible just a few years ago.
Wow, that's incredible. So we're talking about being able to measure magnetic fields at the atomic level. What could we do with that kind of sensitivity?
It opens up a whole new world of possibilities in fields like materials, science, and condensed matter physics. Imagine being able to map the magnetic fields within a material with atomic resolution. We could study the properties of exotic materials, understand how magnetic fields influence chemical reactions, and even explore the fundamental nature of magnetism itself.
So we could unlock the secrets of how magnets work at the most fundamental level. Sign me up for that research team. But I know you're also excited about the potential of NV centers in biological imaging. Tell me more about that.
Using NV centers for biological imaging is a really exciting area. Remember how we talked about using NV centers to detect biomarkers? Well, their quantum sensing ability takes this to a whole new level.
Okay, I'm intrigued. How so?
Instead of just detecting the presence or absence of a molecule, we can actually use NV centers to map the distribution of molecules within a cell or tissue with incredible precision. We can see where specific proteins are located, how they interact with each other, and even how they move around over time.
So it's like creating a 3D map of a cell, showing all the players and how they interact in real time. That would be revolutionary.
Exactly. It would be like watching a tiny cellular city in action with all its intricate workings laid bare. This kind of imaging could revolutionize our understanding of cell biology, disease processes, and even drug development.
Wow. It's amazing how something as seemingly simple as an imperfection in a diamond can unlock so much potential. It really highlights the power of harnessing the strangeness of quantum mechanics.
I completely agree. And the most exciting part is that we're only just beginning to explore the possibilities of NV centers. As researchers continue to push the boundaries of this technology, we can expect even more groundbreaking discoveries and applications in the years to come.
Well, deep divers, that brings us to the end of our exploration into the fascinating world of NV centers and NV-NMR spectroscopy. We've covered a lot of ground today, from the basics of how ND centers work to their incredible applications in nanoscale imaging, quantum sensing, and even potentially single molecule studies.
We've seen how these tiny imperfections in diamonds are revolutionizing our ability to study the world at the atomic level, opening up new frontiers in fields ranging from materials, science, and biology to medicine and quantum technology.
I don't know about you, but I'm feeling incredibly inspired by the ingenuity and creativity of the researchers who are pushing the boundaries of what's possible with this technology. It makes me wonder what other secrets of the universe are waiting to be unlocked by harnessing the power of quantum mechanics.
It's a question worth pondering. And who knows, maybe one of you listening out there will be the one to make the next big breakthrough in this exciting field.
Until next time, keep exploring, keep questioning, and keep diving deep into the fascinating world around us.